A hot air balloon is rising straight up from a level field, is tracked by a rangefinder 500 feet from the liftoff point. At the moment, the rangefinder's angle of elevation is pi over 4. The angle is increasing at a rate of 0.14 radians per minute. Determine how fast the balloon is rising at that moment. Okay, so at that moment in time. So we are given the change in angle Okay, so that's the rate at which the angle is changing. We can draw ourselves a little diagram. Say, well, here's the angle, here's the height of the balloon. The rangefinder is 500 feet from the liftoff point, right, and the balloon's going straight up, so no wind. And from this, we can say, well, the tangent of theta is opposite over adjacent, or h over 500, which leads to an expression for h of 500 tan theta. Because what we know, what we want to find is how fast the balloon is rising, right? So it's dh by dt is what we want to find, right? The rate of change of height with respect to time. Okay, so let's do that. I think I have to move this like this. Oh, wait.
How do you know that it's
Got a drag. This is a drag.
because it's something related to something, right?
Okay.
A sign.
So, starting with an expression for h, right? This is what's relating h and theta, right? Remember, related rates. So we need something to relate the quantities, which are the angle and the height. We take the derivative with respect to time of both sides, giving us dh by dt is equal to, and the derivative of tangent is secant squared, right? So we got the 500 still, it's a constant. So it's 500 secant squared theta d theta by dt. Okay, so first, relate the two quantities with an equation. Draw a diagram, right? Draw a picture. Oh no, by the way, on yesterday's one, there are, if you look on the green sheet for number, whatever it was, number 8, the correct answer is written in there, right? So for those of you who are upset about the book and the incorrect answers, if there's an incorrect answer in the book, it is on the sheet corrected, okay? So, right, so we drew a diagram, we got an expression for h, we related it to theta, we found the derivative, and now we just sort of plug in. So what do we know? Well, when theta is equal to pi over 4, and we know that d theta by dt is 0.14, then we plug that in, right? So let's do that. So dh by dt, which is what we want to find, is 500 times the secant of pi over 4 squared. That's find the secant and then square it, right? That's what sec squared means. Times 0.14. Okay, so let's drag that down. All right, so secant is 1 over cos, right? Reciprocal of cosine. The cosine of pi over 4 is root 2 over 2. But it's a little more helpful in this case to think of it as 1 over root 2. Right? It's your alternate form. Because we're going to reciprocate it. I don't even know if that's the word. Probably not. We're going to find the reciprocal of it. And the reciprocal of 1 over root 2 is root 2, which when squared is 2. So this is 2. Okay, so you got that. Here, let's just scribble this over here. Okay, so the secant of pi over 4 is 1 over cos pi over 4, which is 1 over root 2, which is root 2. Okay, then you square that, you get the 2, and we got 1,000 times 0.14, which even people without a calculator should be able to do. And we get 140, and our units are, I'd slide this up, but I can't really do that easily. So it was in feet. The angle was changing in radians per minute, so we have feet per minute. 140 feet per minute is the rate at which the balloon is rising when the angle of the rangefinder is pi over 4 degrees, right? At that moment in time, yes.
On the test, is like, are we going to be expressing it in fractions, or are we going to be expected to do it in test?
Well, the 0.14 was
like,
given to you.
This one's easy, but I mean, like, other ones.
So I would never expect you to do something that you would obviously have to use a calculator for. So when we end up with an answer, it's like, you know, root 3 over root 22 or something like that. That's the best you can do on a test, right? I may then go on to state it as, just to put it in a context where you can sort of imagine it a little better than that kind of abstract number. But one down, 3 to go. A boat is pulled toward a dock by a rope through a ring on the dock 6 feet above the bow. The rope is hauled in at the rate of 2 feet per second. Okay. Now I almost think, do you really need a diagram to do this? So I'm going to draw the diagram just because it took me a while to sort of figure out what this was exactly talking about. We've got two things, right? A, how fast is the boat approaching the dock when 10 feet of rope is out? And B, the angle between the rope and the dock is changing when 10 feet of rope are out. Yeah, 1 second. No, wait, it's okay, so we want to find two things, right? So here's the diagram. This is what it looks like. So here's this dock, right? And here's the water, and there's a ring on the dock, and there's a rope, and here's the boat. And there is a rope attached to the boat, and it's pulling in, right? So there's somebody up here. Like this is water down here, and there's the dock, right? So you're up. So it's as if I'm standing on the dock here, and there's a ring there, and the boat's down on the floor, and I'm pulling on this rope, okay? All right, that's... Okay, so, right? Boat's on the floor, I'm standing on the desk has a ring through it, there's a rope, and we're pulling on the rope along the dock, and it's pulling the boat in. Okay, so we have some quantities here, let us list those quantities. So let's call this L, let's call this X, let's call this H. Okay, and we actually have some numbers for that, right? So the ring on the dock is 6 feet above the bow, so this H is equal to 6. And we're not going to put the 10 on there just yet, right? But the L is going to be 10, right? It's 10 feet of rope that's out. And, right, so we're going to do part A. So if we're going to relate these guys, okay, we know from Pythagorean theorem, right, good old Pythagoras has told us that L squared, so by Pythagorean theorem, no, this is A, L squared is equal to x squared plus 6 squared. Okay, so the 6 isn't changing, right? The bow of the boat is always 6 feet below the dock. It's not going to get hauled out of the water. But the L and the X will be changing. And at what rate are they changing? Well, okay, so let's go over here. So we know that the length of the rope, that rope is being hauled in at 2 feet per second, right? So that's going to be negative 2 feet per second, right? Because the rope is going to get shorter. Okay, so the length of the rope is decreasing at the rate of 2 feet per second. So now it's 10 feet, and a second from now it'll be 8 feet, and then and so on. Okay. What else do we want here? Well, okay, when there are 10 feet of rope out, okay, so we know that x squared is equal to L squared minus 6 squared. because we're going to need an x at some point, right? We're going to have to know when there are 10 feet of rope out. Although, perhaps I'm doing this. Let's do this first. So let's just take the derivative here, right? So let's go with 2L times dl by dt is equal to 2x times dx by dt. And the derivative of 36 is just 0, right? So here's the expression that relates L and X, right? So we have dL by dt is given to us. Determine how fast the rope is approaching, how fast the boat is approaching. So what we're finding here is dx by dt. Okay, so that's what we want to find. And that's what's going to relate them, right? L squared equals x squared plus 6 squared. So, what? We want dx by dt, right?
Gives you a word.
Let me slide this down. So, dividing out the 2 on both sides, dx by dt is equal to L divided by x times dl by dt. Okay? Just divide both, get rid of the 2. Divide both sides by 2, cross them off. I want to isolate the dx, so I'm going to divide both sides by x. Gives me L over x dl by dt. Yep. Yes, good. No? Okay. So, let's go over here. When L is 10, what's x, right? Because we need to know. We know L is 10, right? We know there's 10 feet of rope out. We just need to know this, and we know this. Right? That was given to us. So we got to get x. Okay, so x equals 1 minus 36, which is 64. That's x squared, actually. And so x is 8. Ignore the minus 8. We do know that x is plus or minus 8, but negative 8 does not make sense in this context because it's the length of a rope. Okay, so dx by dt
That's 64.
is equal to 10 over 8 times negative 2, which is 10 over 4, 5 over 2, negative 5 over 2 feet per second. Okay, so the boat is moving to the dock at negative 5 halves, or some of you might say negative 2.5 feet per second. Because it's going toward, so x is shrinking. Hang on. Okay, and now we want to do part B, right? So B deals with the angle between, what does B deal with? B deals with, determine the rate the angle between the rope and the dock is changing. So that's this angle here, right? Rope, dock. Okay, so we know that should be getting smaller, right? It should be getting closer than, if it's being let out, there's going to be a lower angle, and coming in, it's going to be a higher angle, or smaller angle here. So let's call that theta. So we want to figure out d theta by dt, right? Sorry, the only way I can move this is dragging it down. I don't know why it's only for you guys. Okay, so B. We need d theta by dt. And what have we got? So the scenario we've got is this is 6, this is 8, this is 10, this is theta. But this is x, right? X is equal to 8. So at that moment, x is equal to 8, right? Just in case we need the x again. We need d theta by dt. We know dx by dt, right? So if we can get an expression in terms of theta and x, we can throw that in. So let's do that. I mean, why not, right? We got dx by dt. We calculated it here. And then we'll look at an alternate. So let's say tan theta is equal to x over 6. Okay, so I want to solve for d theta by dt, right? So I'm not going to write this as x equals 6 tan theta. I mean, might as well just take, well, I guess you could. I don't know. Let's just take the derivative of both sides. So the derivative of tan is secant squared, so we get secant squared theta. D theta by dt is equal to 1/6 dx by dt. I guess we could just multiply by 6, right? But I want to get d theta by dt by itself, right? So d theta by dt equals 1 over 6 secant squared theta dx by dt. I suppose we could just write that as cos squared theta over 6, couldn't we? Do you want to? Does it matter? I don't know. No, let's do it. I'm going off book here because I don't have my answer written like that. So okay, I know what the answer is supposed to be. Let's see what we get. Right. So what do we need? We need cos theta, right? So here's our scenario. So at this moment in time, we need the cosine of theta. Well, there's theta. So cosine is adjacent over hypotenuse, right? So cos theta is 6 over 10, right? So we don't do anything fancy here, right? Just cos theta is 6 over 10. So cos theta is 6 over 10, which is actually 3 over 5, right? Yes, might as well reduce it.
Isn't it dx?
Oh, yeah. It's good. Earn your keep. Okay. So, what do we need to know? We need theta. We got theta. We got dx by dt, right? Because we just calculated it, so it's here. Now, some of you might be purists and say, I don't want to do that with the bit, and then we'll look at another way to do it, right? There's an alternate way, because I worked it out twice. Okay, so let's go over here. So d theta by dt. So cos squared, right? That's 3 over 5 squared over 6 times negative 5 halves. Right? Because dx by dt, negative 5 halves. So that's 9 over 150 times negative 5 halves.
No, d theta.
30. Where's that? 3 over 5. That's 9 over 25. Right? Over 6. 50, 30. Oh, yeah, okay. So wait, 9 goes into this. 3, 10. Okay, so we got negative 3 over 20. And it's an angle that's changing, right? So it's going to be radians per how fast? We're doing it in seconds, right? We're holding it in seconds. So negative 3/20ths of a radian per second. And that will work. So the question you have is, but can I do this a different way, right? Like, what if we so really what we need to do is relate two quantities, right? It could be theta and x, or it could be theta and L. Now the reason we can do theta and x is we know dx by dt, we calculated it. However, you might say, that's calculated value, and what if I got that wrong? Then that's going to make this wrong, right? By definition. That's wrong, that's wrong. What if we go with dl by dt, because I know what that is? That was given to me. Okay, so here's an alternative. I'm not going to do the whole thing. Fear not. So, so this is B, or B, relate theta and L. Okay, so here's theta, here's L, right? So L is the hypotenuse, and theta is the angle. So you might want to say, well, okay, how can I relate L and theta? I can use any of the sides, right? Well, let's say we're going to use the 6, because we know the 6, and we're given the L, dl by dt. Forget about the x, right? We're not going to do x here. We want to use L, 6, and theta. So what do we got? Adjacent and hypotenuse. So I can go cosine of theta is, what is it, 6 over L. But you know what would be easier would be to go the secant of theta is L over 6. Okay, and then you just, again, you're going to do the derivative now, right? So you'll do d theta by dt. So the secant, derivative of secant is sec theta tan theta. So you get secant theta tan theta. D theta by dt is equal to 1/6 dl by dt. Okay, so we know this. We can get that, right? We got theta. So we can get secant theta, right? Because we now go back down here. So you get your secant theta. So you plug in for secant theta, you plug in for tan theta, you work them out and then move them to the other side and work it out. And you'll get the same number, right? So it doesn't matter. It doesn't matter what you use. You could use cos theta here and 6/L. It makes no difference, right? Okay. A little planning ahead, though, doesn't hurt. Right, so looking at things and just saying which trig ratio might be better to use, right? It's like doing math is like doing chess, right? You want to look ahead a few moves and just sort of say, if I use this ratio, is this going to cause me problems? Right? Am I going to end up with something that really I don't want to be doing that, or whatever? Man, ma and ma nud. Two sides of a triangle have lengths 15 ma and 20 meters. I think it's 15 meters and 20 meters. The angle between them is increasing at pi/90 radians per second. You could actually probably even imagine that, because you could convert pi/90 to degrees and say, oh, it's this many degrees per second, and you could imagine that better. Who knows? Doesn't matter. Determine how fast, well, it might, I mean, because you kind of relate it back. Remember, the fourth step in problem solving is look back. It's like, does that seem reasonable that it's changing at 300 kilometers an hour? Well, probably not when you look back. Anyways, determine how fast the length, let's draw a picture. Always draw a diagram. So I got a 20 meter side, got a 15 meter side. There's an angle between them, which we will call theta. There's a third side to this triangle. Let's call it x. And we want to know dx by dt, right? Based on this diagram, we're looking for dx by dt. We know d theta by dt, right? This is d theta by dt. We know the rate at which the angle is changing. So we need a relationship between the angle and the side. What relationship might that be? Got two sides in the included angle. There's a law about that. Cosine law. So we're going to use the cosine law. So here's our relation. The cosine law says that x squared is equal to 15 squared plus 20 squared minus 2 times 15 times 20 times the cosine of theta. Okay. So we can simplify this, right? Because we can square the 15 and square the 20 and multiply 2 times 15 times 20. So let's work on simplifying a bit. So 15 squared, you know how to square numbers ending in 5 now, right? Take the number in front of the 5, multiply by the next higher number, and then stick 25 on the end. If you don't believe me, 75 squared is 5625. If you had a calculator, you could try that. What do we got? 30 times 20 or 40 times 60, let's go with 600. Or go 10 times 15 times 4, I don't care. You figure out how to do your own mental math. All right, so this is 625, so x squared is equal to 625 minus 600 cos theta. So at this point when I was solving, I had this bright idea of, well, I will solve this for x and get a square root. And then really, no, you want to take the derivative. You just got 2x times dx by dt. And then you can divide both sides by 2. Otherwise, you've got 1/2 times 625 minus 600 cos theta to the negative 1/2. And that would just be silly. So take the derivative of both sides. So 2x times dx by dt, right, which is what we want to find, right, dx by dt. Is, so the derivative of 625, and the derivative of cos is minus sine, so this will be 600 sine theta. Times d theta by dt, right? Implicitly. Divide both sides by 2x. And we get 300 sine theta over x times d theta by dt, which we know We just need to figure this out. I know,
And when you do it the second time.
right? Good. Say it louder. Make sure that gets picked up by the. Yeah, and how'd you do your first time through? Was that in that video, the stuff calculus students never say? I hope I fail so I can take it again. At which point the prof says, don't worry, half of you will. There, I'm not going to mention this guy's name because it's embarrassing. There's an engineering math course at a university I went to back east in Hamilton, Ontario. And I never took it. I wasn't in engineering. I was in applied math, computer science. But all my friends took it. And these were bright guys. And they sort of scraped through with like 60s, right? It was like a full year engineering math course. And these guys who were 80% plus masters were getting like 60s. And one guy failed it like 4 times. Like seriously. He actually got a job in the engineering as an engineering tech or something in the faculty, just so he could keep coming back year after year to take this course. And after he passed it, they retired the course. They said, seriously, that's it. We're never going to teach this.
That's like a jersey.
Yeah. I don't know why. I don't know if it had anything to do with him or whatever. But. Okay, anyways. So we need x, right? We need x when the angle between the sides is pi over 3. Okay? So that's the missing piece of the puzzle. Right? Somewhere, yes. We need x. So we need x when theta is pi over 3. Now, luckily we have a pretty simplified form right here. We can just plug into this, okay? So x squared is equal to 625 minus 600 cos pi over 3. Now, we did not pick that angle on accident, right? What is the cosine of pi over 3?
1/2.
1/2, right? So x squared is equal to 625 minus 300, and x is equal to the square root of 325. Okay, so all we got to do now is plug in down here, root 325 for x, theta for theta, pi over 3 for theta. Right? So over here, we now know this. That's what we had to calculate. We knew the angle, and we know d theta by dt. So plugging in, we get 300 sine pi over 3. So cos pi over 3, then we know what sine pi over 3 is. Over root, horns in the forest. It's like Game of Thrones, right? You expect to hear something like that. And what was d theta by dt, right? It was like pi over 90. Was it increasing or decreasing? I think it was increasing, right? Yeah. Okay, good. Because it was decreasing, and then I have to make that negative, right? We'd have to got to get your directions. Okay, what's the sine of pi over 3? Root 3 over 2, right? We know that because if the cos of pi over 3 is 1/2, then the sine of pi over 3 is root 3 over 2. Okay, so what do we got? 300 times root 3. Oh, well, let's just throw the 2 down here. And I don't know what. Well, 30 goes into that 3 times, and into that 10 times. 2, 5, and 3 doesn't go into 325, right? So what have we got? 5 pi root 3. That? No. Oh, wait a sec. Root 325. Yeah, hang on. Isn't this like 25 times 13? Okay, so that's a 5 root 13, so the 5s are gone. All right, so we got pi root 3 over 3 root 13. And the units on that are meters per second. Okay. Now, of course, you'd never leave it like that, right? So you'd write root 39 pi over, 13? No, 39. 39 meters per second which if you want to translate that into English, it's about 0.50 meters per second. So about half a meter per second. Is the length at which the third side is changing. Okay. One more. And then you too can have the pleasure. A beacon located at a perpendicular distance of 300 meters from R on a straight shoreline revolves at one revolution per minute. Determine how fast its beam sweeps along the shoreline at the point 400 meters from R. So imagine there's some little beacon sitting out at sea a little bit, like 300 meters from the shoreline, and you're at this point R. So here's the shoreline. Here's this point R. Here's the beacon out here, beacon, which is 300, and this is 300 meters. And let's call this X. That's going to be 90. That's theta. And then there's a point.
You said it now.
Let's call that S. So we want to know when X is 400, right? But we're not putting 400 in there just yet, okay? So we're saying, and what do we want to find? How fast its beam sweeps along. So we want to know the rate of change of theta, right? Based on X. So we need something that relates theta and X. What could we use? Well, there's theta. X is opposite. 300 is adjacent. It's only tangent, right? So tan theta is X over 300. What else do we know? This one here. D theta by dt. One revolution. How much of a theta is one revolution? Or how many thetas? 2 pi thetas. So it's moving at 2 pi radians per minute. Okay, that's the speed at which it's going. That'll be one revolution is 2 pi radians, so 2 pi radians per minute. How fast its beam sweeps along. So that's dx by dt. Right, so we want to know the speed at which it's moving along the shoreline. Okay, derive away. So sec squared theta. This is a common thing. You ever notice in trig how a lot of it was tangent ratio? So we don't usually care about the hypotenuse for some reason, but opposite adjacent. All right, what do we got? 1/300th. Okay, and what are we looking for? We're looking for dx by dt, so let's multiply both sides by 300. dx by dt is 300 secant squared theta d theta by dt. Okay, so we need the secant of theta. All right, so there's theta. When this is 400. So when if that's 300, that's 400, what's this? 500, right? Y'all know that. It's a 3, 4, 5 triangle. Or a 300, 400, 500 triangle, right? So otherwise you can use Pythagorean theorem and get 500 and then be embarrassed. Because saying, oh, right, yeah, should have figured that one out. Okay, so secant of theta. What's secant? So cos is adjacent over hypotenuse, and secant is hypotenuse over adjacent, right? So secant theta is hypotenuse 500 over 300. Or let's call that 5/3. Okay, so we've got this, and we've got this. We just got to plug in. So it's 300 times the secant of theta, which is 5/3 squared, times d theta by dt, which was 2 pi. So what do we got? 600 pi, so 600 times 25 times pi over 9. 200. 200 times 25. Well, that's like 2,500 doubled, right? So that's 5,000. 5,000 pi divided by 3. Oh wait, 200 times 25. 200? Oh yeah, 5,000 pi over 3 meters per minute. Whatever that is. You say pi is 3, it's like a little bit over 5,000 meters per minute. Which would be a little bit over whatever that is divided by 60 meters per second. Okay. Done.